Okay, so in last class session, we discussed limiting reactants and methods of calculating limiting reactants, such as the product method. So in today's session, what we're going to do is we're going to do a few more limiting reactant problems and then discuss how we can apply this idea of limiting reactants and theoretical yields to experimental conditions and calculate values such as percent yield. So let's do an example now where we have a word equation and we have to convert the word equation into a chemical equation and then identify the limiting reactant and finally determine the mass of product expected from this reaction. So 50 grams of sodium bromide. So we have sodium plus and Br minus. We cross our charges, that gives us NaBr. Okay, silver nitrate. Silver is a fixed charge transition metal, silver plus. Nitrate is NO3 minus. We cross our charges, and that gives us AgNO3. That in turn yields silver bromide, Ag plus, Br minus. We cross our charges, that gives us AgBr. And then sodium nitrate, we have Na plus, NO3 minus. We cross our charges, and that gives us NaNO3. Okay, perfect. So we have our equation set up, and I'd like you to type in the chat now, is this equation balanced? Is this equation balanced? Yep, it's perfectly balanced. Okay, so now we can begin to use it. So what we're going to do is we're going to, if we're asked to calculate the mass of silver bromide produced, first things first, we're going to go from the grams of one of our reactants, such as sodium bromide, to the grams of silver bromide. And in order to accomplish that conversion, we're going to go from grams to moles of sodium bromide, from moles of sodium bromide to moles of silver bromide, and then finally from moles of silver bromide to grams of silver bromide. Okay, with that established, if we have 50.0 grams of sodium bromide, we know that in 1 mole of sodium bromide, we have 22 gram per mole plus 79.9 gram per mole. This is just a molar mass calculation that we've done time and time again. Now for something interesting, now for something that's really important and the backbone of this chapter. How many moles of silver bromide do we produce per mole of sodium bromide that we consume? What's our mole to mole ratio? What is our mole to mole ratio? 1 to 1, exactly right. And then finally, we know there are how many grams of silver bromide in 1 mole. Would someone like to volunteer in the chat just to make sure everyone's comfortable with molar mass calculations? Would someone mind providing in the chat the molar mass of silver bromide? $187.7. Okay, perfect. So now that we have this set up, we can punch this into our calculator. So let's do just that. So here we're calculating the theoretical or expected yield of silver bromide if we used up all of our sodium bromide. So we have 50 divided by 101.9 times 1 over 1 times 187.7. And that gives us an expected mass of 92.1 grams of sodium bromide. However, are we done with this problem? Can we just stop here? Is this the only calculation that we have to do? Are we done? So reading through this problem, we reacted 50 grams of sodium bromide and 100 grams of silver nitrate. And as the students in the chat are immediately pointing out, we're not done. We still need to check to see if silver nitrate is limiting. So to do that, we're going to go from the grams of silver nitrate to the moles of silver nitrate to the moles of silver bromide to the grams of silver bromide. Okay, so now that we have 100.0 grams of silver nitrate, we know that in 1 mole of silver nitrate, again, would someone like to volunteer in the chat the molar mass of silver nitrate? Just to make sure everyone's comfortable with calculating these molar masses quickly and efficiently. What is the molar mass of silver nitrate? What is the molar mass of silver nitrate? 169.87. Very good. Again, we're just adding the mass of silver to nitrogen to the mass of oxygen times 3. Now, again, really critically, what is our mole to mole ratio? How many moles of silver bromide do we produce per mole of silver nitrate? What is our mole to mole ratio? One to one again, yep. And you know, just for additional efficiency, if we want to calculate the mass of product, we already calculated the molar mass up here. We know that there are 187.7 grams of silver bromide in 1 mole of silver bromide. So now that we have all this information established, let's now punch this into our calculator and determine the expected yield of product if we use up all of our silver nitrate. So punching this into our calculator, we get an expected yield of 110.49 grams of silver nitrate. Oh, whoops, sorry, of silver bromide from silver nitrate. So if we compare our two yields, which reactant is limiting? Which reactant produces the least amount of product? Which reactant, when completely consumed, produces the least amount of product? Which reactant is limiting? Sodium bromide, exactly right. So we know that sodium bromide is limiting. So this 92.1 grams is the mass of product that is actually generated. Okay, we're going to use that information. Now, in our next step, we know that if we start off with 100.0 grams of silver nitrate, if we want to figure out the excess silver nitrate, what we're going to do is we're going to subtract, and we're going to take the mass of product and we are going to convert it into the mass of the excess reactant. So we know we have 1 mole of silver bromide per 187.7 16.7 grams. We know, based on our mole to mole ratio, we have 1 mole of silver nitrate consumed for every 1 mole of silver bromide that reacts. And then we know that we have 169.87 grams per 1 mole of silver nitrate. So then, punching this into our calculator, we can figure out if we make this amount of silver bromide, how much silver nitrate did we actually use up? Again, you use the mass of product generated from your limiting reactant and you convert it to the mass of excess reactant consumed. So punching this into our calculator, we get 16.7 grams of silver nitrate excess. Does this example make sense to everyone so far? Does this example make sense to everyone so far? Any questions on this example? Any questions on this example? If not, let's work on, so this is just extra space for the problem in case we needed it. Let's work on another problem. In this case, you're given a chemical equation in word form. You're asked to identify the limiting reactant, identify the mass of water produced from this reaction, and I'd like you to identify the mass of excess reactant left over. So let's take about 6 to 7 minutes to work through this problem. And in about 3 minutes, we'll come together and we will discuss the balanced chemical equation. So make sure you're able to draw and write out the balanced chemical equation from the word formulas. And we'll discuss, to the previous problem, sure. And let me know when I can scroll down for those who are still taking notes from the previous problem. May I scroll down to the example that we're working on right now? I just want to check that everyone was able to finish taking down their notes. Perfect. Okay, so let's spend about a total of 6 to 7 minutes on this example. And in about 3 minutes, we're going to discuss the balanced chemical equation. Remember, the key to stoichiometry problems is determining the balanced chemical equation. Without the chemical equation, you cannot progress further in solving these problems. This would be the second 6.8.4 quiz. I can double check that right now. Don't be shy to submit your responses, both in the chat, verbally, or via Canvas. And if you have any questions at all, don't be shy to unmute and ask your question verbally. Ask your question in the chat, or to submit any questions that you have via Canvas. and we'll discuss the balanced chemical equation in about another 2 to 3 minutes. And in Canvas, this is the first 6.8.4 quiz. It's the one with 3 questions. And in fact, we already see a few responses via Canvas. Let's try to get a few more responses via Canvas in the chat. And if you have any questions at all, do not hesitate to ask. And we'll discuss the balanced chemical equation in about another 2 minutes. And if you have a proposed balanced chemical equation, don't be shy to type it in the chat, and we'll discuss this the first part of this example, just getting our balanced equation, in about another minute. Okay, so let's discuss the balanced equation for this example. So first, let's write out the formulas. So calcium hydroxide, so we have calcium 2 plus and OH minus. So we cross our charges, and that gives us CaOH2. Okay. Hydrochloric acid. Would someone like to volunteer in the chat? What is the formula for hydrochloric acid? What would the formula be for hydrochloric acid? HCl, yep. So hydrochloric acid is a binary acid derived from hydrogen and chlorine, and that gives us HCl, aqueous. Okay. Calcium chloride, we have calcium 2 plus, Cl minus. We cross our charges, and that gives us CaCl2. Okay, and then water is H2O. Now, looking at this equation, is the following chemical equation balanced? Is the following chemical equation balanced? No, the equation is not balanced. So if we look, we see on the right-hand side, we have 2 chlorines and we have 2 hydrogens. While on the left-hand side, we have 2 hydrogens plus 1 hydrogen, which would give us 3, and we have 1 chlorine. So my question to all of you is, what times 1 would give us the 2 chlorines that we need? What coefficient do we need in front of hydrochloric acid? What times 1 would give us 2 chlorines? What times 1 would give us 2? 2, yep. So now we have a total of 4 hydrogens, okay? So then to balance hydrogen, 2 times what would give us 4 hydrogens? 2 times what is equal to 4? 2, exactly right. Okay, perfect. So now that we have our balanced equation in place, I'd like you to use this balanced equation and the mass of each of our reactant, which is 100 grams. And I'd like you to determine the limiting reactant and then calculate the mass of product and calculate the mass of excess reactant remaining. And we'll spend about 4 to 5 minutes on this next part. And again, don't be shy to submit your responses in the chat or via Canvas. And we'll discuss these examples momentarily. It doesn't matter, but since the problem is asking for you to calculate the mass of water for efficiency, it would be reasonable to convert each of your reactants into the mass of water expected if that reactant is consumed. Does that make sense? But you could technically calculate the expected mass of calcium chloride to identify the limiting reactant, but then you'd have to do another calculation to calculate the mass of water. So it's easier just to calculate the mass of product asked for in the problem to determine your limiting reactant. And we'll discuss in about another 4 minutes. And I want to see a reasonable pool of responses via Canvas and in the chat before we discuss. And if there are any questions at all, don't hesitate to ask. And if you have any proposed assignments for what species is the limiting reactant and what mass of product do we expect from this reaction, again, don't hesitate to ask. And we'll discuss this example in about another 3 minutes. Let's try to get a few more responses in the chat and via Canvas, just so that way I can see that everyone's comfortable solving these problems, especially because these problems will be quite common on your exam. So you want to be able to solve them properly. And if there are any questions, again, don't hesitate to ask, and we'll discuss this example in another 2 to 3 minutes. And the responses I see in the chat look good so far. Yep, the responses I see in the chat look perfect so far. Let's try to get a few more responses in the chat and via Canvas, and we'll discuss in about another 1.5 to 2 minutes. And if you need more time, and if you're just almost there to a complete response, don't hesitate to let me know in the chat if you need a little bit more time. It looks like the class needs probably about another 2 to 3 minutes, but the responses I'm seeing so far in Canvas and in the chat look really good. So let's try to get a complete solution for these problems, and then we'll discuss momentarily. Let's try to get a few more responses, and if there are any questions, we'll discuss this example in about another 1 to 1.5 minutes. Let's try to get the majority of the class submitting a response. And if you don't want to submit a response via Canvas, don't be shy to submit your response in the chat, just so that way I can check up and seeing how everyone's doing. And the responses I'm seeing so far in the chat look perfect. Try to get a few more responses before we discuss. And at the bare minimum, let's at least get a few questions if you have any questions on these examples. So we'll keep working through this problem and we'll discuss momentarily. So I see a reasonable pool of responses so far. So let's discuss this example. So first and foremost, let's go from our mass of calcium hydroxide and let's calculate the mass of water expected. So to do that, we're going to go from the mass of calcium hydroxide to the moles of calcium hydroxide. From the moles of calcium hydroxide, we can calculate the moles of water. And then from the moles of water, we can calculate the grams of water. Okay, so we have 100 grams of calcium hydroxide. And I'd like to have the class's help. In 1 mole of calcium hydroxide, what is the molar mass of calcium hydroxide? How many grams are present in 1 mole of calcium hydroxide? We actually are given that in the problem, 74.09 grams. But if you wanted to test your ability to calculate molar masses, it would be good to try to calculate this from scratch. Okay, now we look at our mole to mole ratio. How many moles of water do we produce per every mole of calcium hydroxide that we consume? What is our mole to mole ratio? What is our mole to mole ratio?
2:1.
Yep, exactly right. We have 2 moles of water per every 1 mole of calcium hydroxide. Okay, and then for water, we have 18 grams of water per every 1 mole of water. And this is why I like the one-line method, just the reason why I like using the one-line method of unit conversions, because we can write everything out in 1 line, it's easy to audit, and it's easy for us to check in our calculator. So punching this into our calculator, we get an expected mass of 48.6 grams of water, respecting the fact that our input had 3 sig figs, since there's a dot at the end of the 100. Now, we're not done because we still need to figure out the mass of water expected from our other reactant. So we're going to take our 100 grams of hydrochloric acid and we're going to perform the same conversion where we go to moles of hydrochloric acid, then to moles of water, and finally to the grams of water. So we're trying to calculate the mass of product expected if we completely consume all of our hydrochloric acid. So if we have 100 grams of hydrochloric acid, we know that in 1 mole of hydrochloric acid, looking at our provided data, we have a mass of 36.46 grams. Now, checking our chemical equation, how many moles of water do we produce per mole of hydrochloric acid? What is our mole to mole ratio looking at our chemical equation? So to explain why we're using the ratio of water to hydrochloric acid and water to calcium hydroxide, in the problem we're asked to calculate the mass of water generated from the reaction. So we need to convert the mass of each of our reactants into the mass of water. Did that answer your question? Perfect. So let's answer this next critical aspect of this stoichiometry problem. What is the mole to mole ratio of the moles of water, our product, to the moles of hydrochloric acid, our reactant? What is our mole to mole ratio? What are the coefficients? Is it 1 to 1, 2 to 1, 3 to 1? What's our mole to mole ratio? Yeah, 1 to 1 to 1. Yes, that's fine. Writing straight from our chemical equation, I'd write it as 2 to 2, but 1 to 1 is also perfectly fine. Yeah, the 2 to 2 simplifies to 1 to 1. Yeah, that's more than okay. Again, we read off our mole to mole ratio from our reaction coefficients. Finally, we have 18 grams of water per every 1 mole of water. And punching this into our calculator, let me pull up my calculator. Okay, so we have 100 over 36.46 times 18. That in turn gives us 49.4 grams of water. Okay, so looking at our two reactants, which reactant produces the least amount of product? Which reactant generates the least amount of product? Hydrochloric acid or calcium hydroxide? Which reactant makes the least amount of product? Which reactant is limiting, in other words?
Calcium hydroxide.
Yep, exactly right. Because it makes the least amount of product, we can conclude that calcium hydroxide is limiting. Ergo, we only make roughly 48.6 grams of water. Now, if we want to calculate our excess reactant, what we're going to do is we're going to take our 100 grams of hydrochloric acid and we're going to subtract our mass of water, and we're going to convert this mass of water into the mass of hydrochloric acid consumed. So to do that, we know that in 1 mole of water, we have 18 grams. We know, and again, we've already seen these unit mole to mole conversion factors. We know that we consume 2 moles of hydrochloric acid for every 2 moles of water. Okay. And then finally, we know that we have 36.46 grams of hydrochloric acid in 1 mole of hydrochloric acid. And if we punch this into our calculator, so we have 48.6 over 18 times 36.46 minus 100. And that gives us 1.3 grams of hydrochloric acid in excess. This is how much hydrochloric acid is left over at the end of the reaction. Does this make sense to everyone so far? Does this make sense to everyone so far? Any questions so far? So these are the types of problems that you'd be expected to answer on an exam. Okay, so we have some additional space here, but we didn't need it in this case. Okay, so now to apply what we've learned, I have given you an equation in word form, and I'd like you to calculate the expected mass of product generated from the following reaction. Now, one thing that I want you to use this problem as a tool to check. Notice these molar masses. I'd like you to try to calculate the molar mass from scratch. So I'd like you to try to calculate the molar mass from scratch for this problem, and just make sure that your formula is written correctly. Mercury is a little bit of an oddball in terms of its chemical formula. Mercury is a little bit of an oddball in that Hg2 2+ is considered mercury 1. So take a few minutes to work on this example. We'll take about 3 to 4 minutes and try to write out a balanced equation. And then we'll take a few more minutes and try to solve for the mass of product expected. Now, one thing I do want to emphasize, if your result from the previous problem was a little bit different, don't worry. I'm mainly looking that your logic is set up correctly. And I can't see why your answer would be so different. Let me try punching it into my calculator one more time just to check. Oh, yeah, this should be 1.56 that we in turn round to 1.6 grams of hydrochloric acid. Yep. I think I truncated the last part of our molar mass. So there was a small amount of result drift. If you're provided a molar mass, make sure to use all of the digits provided. But I've set up the Canvas quizzes such that the tolerances are wide enough where if you happen to make a rounding error, it will not impact your final result. And if your work is set up perfectly and your response at the end after you punched into your calculator is a little bit off, then you won't lose a ton of points. Okay, so let's work on this next example. Let's try to write out a balanced chemical equation for the following reaction. And then we'll discuss the balanced chemical equation and discuss writing out our balanced chemical reaction in about 3 to 4 minutes. And the responses I see for the coefficients for the balanced chemical equation look perfect so far. Let's keep working through this problem, and don't be shy to message me in the chat your proposed balanced chemical equation, and we'll discuss this example in another 2.5 to 3 minutes. Let's try to get a few more responses in chat for the proposed balanced chemical equation for this reaction. Remember, in order to do stoichiometry calculations, you need a balanced chemical equation. Without it, you can't really progress. And we'll discuss in about another minute. Okay, so let's discuss this example. So first, for potassium chloride, we have K plus and Cl minus. Let's cross our charges. That gives us KCl aqueous. Mercury 1 nitrate. The reason why I gave you the molar masses was because mercury 1 is a bit of an oddball. It's written as Hg2 2 plus. Nitrate, we have NO3 minus. We cross our charges and we get Hg2 NO3 2. So this is mercury 1 nitrate. And you can prove this to yourself if you try calculating the molar mass. So let's do just that. So if you calculate the molar mass of mercury 1 nitrate, you'll notice it matches the given molar mass of 525. Let's continue on now. React to yield, we draw a reaction arrow. Mercury 1 chloride, we have Hg2 2 plus, Cl minus. We cross our charges. That gives us Hg2 Cl2. And then potassium nitrate, we have potassium plus, NO3 minus. We cross our charges, and that gives us KNO3. Okay, so now that we have our equation, my question to all of you, is this equation balanced? Is this equation balanced? No, no. So looking at the left-hand side, we have 2 chlorine. Oh, sorry, we have 1 chlorine. Looking at the right-hand side, we have 2 chlorines. So what times 1 would give us 2 chlorines? What times 1 would give us 2 chlorines? What times 1 would give us 2? 2. Okay. There we go. Now, we also have 1 potassium times 2, which gives us 2 potassium ions. If we have 1 potassium ion on the right, 1 times what would give us 2 potassium ions? What coefficient do we need for potassium nitrate? What coefficient do we need for potassium nitrate?
2.
2, yep, perfect. So now that we have our balanced equation, let's take about 5 minutes and let's try to calculate the expected mass of mercury 1 chloride if we completely used up our limiting reactant. So let's work through this example, and don't be shy to submit your responses via Canvas quiz 6.8.4 or in the chat. And if you have any questions, don't be shy to submit them in the chat or unmute and ask your question verbally. And we'll discuss this example in about 5 minutes. And wow, we already happen to see some responses in the chat that look quite good. Let's spend about another 3 to 4 minutes on this problem, and then we'll discuss. And let's try to get the entire class submitting a response via Canvas or in the chat. Oh yeah, just a correction for mercury 1 chloride, it should be 472.09. I think originally I wrote this problem with mercury bromide, so the molar mass was slightly off. Just a correction in case your calculated value is a little bit different than the response in Canvas. So let's try to get a few more responses in the chat and via Canvas, and then we'll discuss this example momentarily. Thank you again for those who submitted responses via Canvas and in the chat, and we'll discuss this example in about another 2 to 3 minutes. And if there are any questions, don't hesitate to ask. Let's try to get a few more responses via Canvas and in the chat, and then we can discuss. But overall, the responses I see via Canvas and in the chat look perfect. I just want to make sure everyone has enough time that when they're working through this problem, they can come to a reasonable conclusion. So that way, when we discuss, we can compare and correct any potential differences in our solutions. So as I see a reasonable pool of responses via Canvas and in the chat, let's discuss this example. So first, we're going to go from 1.0 grams of potassium chloride to moles of potassium chloride to moles of mercury 1 chloride to grams of mercury 1 chloride. So plugging this in, we have 1 gram of potassium chloride. We know that in 1 mole of potassium chloride, we have 74.55 grams. Now, and this is really important in stoichiometry problems, my question to all of you is how many moles of mercury 1 chloride do we have per mole of potassium chloride? What is our mole to mole ratio? What is our mole to mole ratio?
1 to 2.
1 to 2. We have 1 mole of mercury 1 chloride per every 2 moles of potassium chloride. Now, we also know based on our molar mass, we have 472.09 grams per every 1 mole of mercury 1 chloride. So if we punch that into our calculator, so we have 1 over 74.55 divided by 2 times 472.09. And that in turn gives us an expected mass of 3.2 grams. Of mercury 2 chloride. Okay, let's repeat the same calculation, assuming that we have 1 gram of mercury 1 nitrate this time. We're going to convert this into the moles of mercury 1 nitrate. Once we have the moles of mercury 1 nitrate, we're going to convert it into the moles of mercury 1 chloride, and then the grams of mercury 1 chloride. So if we have 1.0 grams of mercury 1 nitrate, we know that in 1 mole of mercury 1 nitrate that we have, let's look at our molar mass, 525.19 grams. And now for the really critical juncture here, in 1 mole of mercury, let me rephrase that. For the critical juncture, how many moles of mercury 1 chloride do we have per mole of mercury 1 nitrate? What is our mole to mole ratio? What is our mole to mole ratio? What's the mole to mole ratio between mercury 1 chloride and mercury 1 nitrate? 1 to 1, exactly right. For our molar mass is exactly the same. We have 472.09 grams for every 1 mole of mercury 1 chloride. So punching this into your calculator, 1.0 over 525.19 times 472.09. That gives us a mass of 0.9 grams of mercury 1 chloride. So comparing which reactant is limiting? Potassium chloride or mercury 1 nitrate? What reactant is limiting in this example?
The mercury 1 nitrate.
Yep, exactly right. So we actually only generate 0.9 grams of mercury 1 chloride because mercury 1 nitrate is used up first. It's our limiting reactant and it limits the amount of product generated. Does this example make sense to everyone? Any questions on this example? If not, let's keep going. I just left some excess space in case we needed space. Let's do another example. Again, just really wanting to make sure that we have this. Let me check. I can double check the calculations and punch this into the calculator one more time. So we have 1.0 over 525.19 times 472.09. And that gives us 0.9 grams. I don't see an issue with this calculation when I punched into my calculator. If there's a small amount of drift, because this answer is rounded, that's perfectly okay. As long as your setup is correct, the answer should be the same unless there is an input error. Let's work on another example. Let's really make sure that we have this skill set down. And let's look at the following example where we have the reaction between iron 3 chloride and silver nitrate. I'd like you to write out the balanced equation I'd like you to tell me what mass of silver chloride will be generated from this reaction and what mass of excess reactant remains at the end of the reaction. So let's take about 3 to 4 minutes to write out a balanced chemical equation, and then another 4 to 5 minutes to solve using stoichiometry for the mass of product expected and the mass of excess reactant remaining. So we'll discuss this example balanced chemical equation in about 3 to 4 minutes. And if you have any questions, don't be shy to message me in the chat or unmute and ask your question verbally. And if you happen to come upon your final response for this question, don't be shy to submit your responses via Canvas quiz 6.8.5. So we'll discuss this example in about 3 to 4 minutes. First things first, I want you to get a balanced chemical equation. That's really the key for these stoichiometry problems. So don't be shy to submit your proposed balanced chemical equation into the chat or unmute and propose your solution verbally. And then we'll discuss this example in a few minutes. And we'll discuss this example in about another minute and a half. And don't be shy to submit your proposed solution for the balanced equation, and we'll discuss this example in about another 30 seconds. And don't be shy to submit your responses for the balanced chemical equation in the chat. Really is the core of these problems. So let's discuss this example. So iron 3 chloride. So we have Fe3 plus and Cl minus. We cross our charges. That gives us FeCl3. Silver nitrate. We have silver plus and nitrate, which is NO3 minus. We cross our charges and we get AgNO3. Okay. At the end of this reaction, we get silver chloride and iron 3 nitrate. Again, Fe plus, NO3 minus, cross our charges. Silver chloride, silver plus, Cl minus, cross our charges. And now, just to take a look at this problem, is this equation balanced? Is this equation balanced? Is this equation balanced? Make sure you always ask that question. Whenever you see a chemical equation, it clearly is not balanced. We see 3 chlorines on the left. We have 1 chlorine on the right. So what times 1 would give us 3 chlorines? What coefficient do we need for silver chloride? What coefficient do we need for silver chloride? What times 1 would give us 3? What times 1 would give us 3? What coefficient do we need for silver chloride? 3, yep. Okay, now we have 3 silver atoms on the right. We have 1 silver atom on the left. So what times 1 would give us 3 silver atoms? What times 1 would give us 3 silver atoms? What coefficient do we need for silver nitrate? Three, yep, exactly. Perfect. So now that we have our balanced chemical equation in place, let's try to use this chemical equation to calculate the expected mass of product. So let's take about 5 to 6 minutes to work through this example, and let's use stoichiometry to calculate the expected mass of product, identify our limiting reactant, and then calculate the mass of excess reactant remaining. So we'll discuss this example in about another 5 to 6 minutes. Don't be shy to submit your responses via Canvas or in the chat. I already see a few wonderful responses via Canvas, and let's try to get the majority of the class responding, so that way I can get a sense of where everyone's at and design additional examples if needed to help us through this concept. So we'll discuss in about 5 to 6 minutes, and let's try to get a few more responses in the chat. And don't be shy to submit your proposed responses for the expected mass of product generated from this reaction in the chat or via Canvas. And as I see a reasonable pool of responses via Canvas, let's try to get a few more student responses via Canvas and in the chat, and we'll discuss in about another 3 minutes. I'm really glad to see that everyone's getting used to these stoichiometry and limiting reactant problems, as these really are the backbone of general chemistry problem solving. And we'll discuss this example momentarily. And the responses I see in the chat for the expected yield of product look perfect so far. And we'll discuss in about another 2 minutes. Let's try to get a few more responses and then we'll discuss this example momentarily. And if you need a little bit more time, again, don't hesitate to ask. I want to make sure that this is simulating the type of problem solving that you'd be performing on an exam. And the mass of excess iron 3 chloride that I see in the chat looks perfect. And we'll discuss this example momentarily. Just a side note, you're welcome to use any problem solving method, be it the ICE or the product method. Really, whatever method works best for you, that's the one that you can use. So let's discuss this example. So first and foremost, we have our balanced chemical equation. Now let's convert. So we're going to go from 18 grams of iron 3 chloride to the moles of iron 3 chloride to the moles of silver chloride to the grams of silver chloride. Okay, so we have 18.00 grams of iron 3 chloride. We know in 1 mole of iron 3 chloride, we have 162.20 grams. In terms of our mole to mole ratio, how many moles of silver chloride do we produce per mole of iron 3 chloride? What is our mole to mole ratio? What's our mole to mole ratio? What is our mole to mole ratio? Is it 1 to 1, 2 to 1, 3 to 1, 4 to 1? What is it? It's 3 to 1 because we have 3 moles of silver chloride for every 1 mole of iron 3 chloride. Okay, and then we also know that we have 143.32 grams for every 1 mole of silver chloride. So if we punch this into our calculator, so we have 18 over 162.20 times 3 times 143.32. That gives us 47.71 grams of silver chloride. But we are not done. Let's do the same calculation for our 16.00 grams of silver nitrate. So we're going to go to the moles of silver nitrate, followed by the moles of silver chloride, followed by the grams of silver chloride. So we have 16 grams of silver nitrate. Okay, we're making progress. We know in 1 mole of silver nitrate, looking at our problem, we have 169.87 grams. And now let's look at our stoichiometry. Looking at silver nitrate, we know we have how many moles of silver chloride per how many moles of silver nitrate. What is our mole to mole ratio? What is our mole to mole ratio? Looking at our chemical equation, what is the mole to mole ratio of silver chloride to silver nitrate? Is it 1 to 1? Is it 2 to 1, 3 to 1? What is it? And don't be shy to type your responses in the chat or respond verbally. What is our mole to mole ratio? This is critical. 3 to 3, yep, exactly right. We have 3 moles of silver chloride for every 3 moles of silver nitrate. Okay. And then finally, we know that we have 143.32 grams per 1 mole of silver chloride. Perfect. So now all we have to do is punch this into our calculator. So we have 16 over 169.87 times 143.32. And that in turn gives us 13.50 grams of, whoops, one moment, sorry about that. There was a small technical issue with OneNote. Let me reshare my screen. Apologies for that. Sometimes OneNote gets slightly unstable when there's a large amount of written text. Okay, so let's punch this into our calculator for the expected mass of silver chloride. And in turn, after punching it into our calculator, we get 13.50 grams of silver chloride. Now, looking at our 2 reactants, which reactant is limiting? Which reactant generates the least amount of product when completely consumed? Which reactant is limiting? Which reactant is limiting?
Silver nitrate.
Yep, exactly right. So then we know that silver nitrate is limiting, and we only generate 13.50 grams of silver chloride. Perfect, perfect. We're almost there. We're almost there. Okay. So now we're going to take our 18.0. So to calculate our excess reactant, we're going to take our 18.00 grams of iron 3 chloride, and we're going to subtract the mass of iron 3 chloride consumed. So we have 13.50 grams. We know in 1 mole of silver chloride, we have 143.32 grams. Additionally, we know, whoops, one moment, let me switch so that the pen is a little easier to see. We know that we have 1 mole of iron 3 chloride per every 3 moles of silver chloride. Finally, we know that we have 162.20 grams per every 1 mole of iron 3 chloride. So punching this into our calculator to calculate the excess mass of iron 3 chloride remaining, we have 13.50 over 143.32 over 3 times 162.20. Okay. And that in turn gives us 12.91 grams of iron 3 chloride remaining. Does this example make sense to everyone so far? Any questions on this example so far? Yes, so for finding the excess, you had a question on that? Yeah, if there are many different methods to go about solving these problems. As long as you're consistently getting the same end result. So let's look at your proposed method. Okay. 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 Yeah, that method's fine. That method is there another step in your method? Yep. Yep, that method's perfectly fine. So that method utilizes the law of conservation of mass, which it's perfectly fine. It will get you the right answer 100% of the time. I haven't seen that method before. It's not very common, but it certainly works and it's logically sound. Yeah. Okay, so let's keep going and let's do another example. Let's do another example. So this is just more excess space. And now let's talk a little bit about chemical reactions in reality. Like what actually happens when you try to run a reaction. From our experience in lab, we know very clearly you often do not recover all of the product from a chemical reaction. Well, there are 2 reasons for that. Chemical reactions are not 100% quantitative. There are competing side reactions that reduce the yield of your desired product. Okay. Additionally, material is also lost during isolation. That's inherent. You can't perfectly transfer material from one location to another. You're always going to lose a small amount. Ideally, not a large amount, but you will lose a little bit. Now, percent yield is the amount of product obtained, which we call the isolated yield, compared to the theoretical yield, assuming the reaction consumed all of the reactants up to the limiting reagent. So throughout this class, this theoretical yield is what we've been calculating all along. The isolated yield is how much you get in your hand at the end of the reaction. So percent yield is defined as isolated over theoretical yield times 100%. So let's look at an example. Suppose you're in the lab, your reaction is expected to yield 200 milligrams of product. You isolated 100 milligrams of product. What would the percent yield be? Just as a back of the envelope calculation. What would the percent yield be if you expect 200 and you only get 100? Would someone like to respond in the chat? If you expect 200 milligrams and you only get 100 milligrams, what is the percent yield, roughly? %, exactly. So the percent yield is our 100 milligrams. So this is our isolated yield, and then our theoretical yield is 200 milligrams times 100%, and that gives us 50%. Okay, not bad, not good. It is what it is. Perfect. So let's do an example together this time where we calculate the theoretical yield and the percent yield for a reaction. So aluminum and oxygen react to form aluminum oxide, okay? So first I'm gonna write my chemical equation, aluminum solid, oxygen gas. Does this make sense so far? Does everyone get where I got those two formulas for aluminum and oxygen? Does that make sense to everyone? Remember, this is in the section of our notes titled Formulas of Elements. This is why I had you on the first exam write out the formulas of different elements, because chemical reactions often will use pure elements. Does this make sense so far? I just want to check with everyone. If there's any part that I need to explain in more detail, do not be shy to ask. Okay, so continuing on, aluminum oxide. So we have aluminum 3 plus, O2 minus. So we cross our charges. So we get Al2O3 solid. Now, is this equation balanced? Is this equation balanced? Is this equation balanced? Are we good to go? No. So what I'm going to do is I'm going to use the least common multiple method. It almost feels like cheating because it works so efficiently. You cross the subscript of one of your compounds containing that element with the subscript of your other compound containing that element. Now we have 2 aluminums on the right, so we need 2 aluminums on the left. Perfect. So now we have a balanced chemical equation. Okay. And we care about the masses of our reactants. So we're going to take our 75.0 grams of aluminum. We're going to convert it to moles of aluminum, then to moles of aluminum oxide, and then to grams of aluminum oxide. Okay, if we have 75.0 grams of aluminum, we know that in 1 mole of aluminum, we have 27.0 grams. And now this is really important. I can't stress this enough. Understanding mole-to-mole ratios will get you through almost the entirety of general chemistry. So how many mole? Yes, there should be 4. There should be 4. Yep, because 2 times 2, 4 aluminums, 1 times 4 would give us 4 aluminums. Yep, exactly correct. Perfect. Good catch. Good catch. Okay, so now that we have our balanced chemical equation How many moles of aluminum oxide are produced per how many moles of aluminum consumed? What is our mole to mole ratio? What is our mole to mole ratio?
2 to 4.
2 to 4, exactly right. Perfect, perfect. So continuing on, we then have to convert the moles of aluminum oxide to grams, and how many grams of aluminum oxide are present in 1 mole of aluminum oxide? What is our molar mass of aluminum oxide? Would someone like to volunteer that in the chat? What is the molar mass of aluminum oxide? Just to make sure everyone's comfortable calculating the molar mass of different compounds. What is the molar mass of aluminum oxide? 101.86, good, good. Okay, so let's punch this into your calculator. So we have 75 over 27 times 1/2 times 101.86. And that in turn gives us 141.47 grams of aluminum oxide. We'll talk about that in a moment, but the mass of aluminum oxide produced, this is known as the experimental or isolated yield. This is how much you actually get from the reaction when you as a student ran this experiment. This 147, this mass of aluminum oxide that we calculate is the theoretical yield. This is the amount that we'd expect if our reaction went to 100% completion and only gave this product. But reactions are not perfect. There are side reactions, you lose material, so the amount that you actually get is always going to be a little bit less than the amount that you'd expect, theoretically. Did that answer your question? Did that address your question? Perfect. So let's do the exact same calculation for our other reactant. So we have 200 grams of oxygen. So we have 200.0 grams of oxygen. We know that in 1 mole of oxygen, we have 32 grams. And now let's look at our mole to mole ratio. So how many moles of So how many moles of aluminum oxide do we produce per mole of oxygen consumed? What's our mole to mole ratio? Is it 1 to 1, 2 to 1, 2 to 4? What is it? What is our mole to mole ratio?
2 to 3.
2 to 3. We have 2 moles of aluminum oxide produced for every 3 moles of oxygen consumed. Further, we know our molar mass is 101.86 grams of aluminum oxide per 1 mole of aluminum oxide. And at the end of this calculation, if we punch this into our calculator, we get 200 over 32 times 2 over 3 times 101.86. And that in turn gives us 424.42 gram. Whoops, that should be 4 grams of aluminum oxide. So which reactant is limiting? Which reactant produces the least amount of product when consumed? Which reactant produces the least amount of product when consumed?
Aluminum.
Aluminum, exactly right. So aluminum is limiting. So we get out 142 grams of aluminum oxide. I only rounded my number at the end because you want to retain as many digits as possible, because sometimes these limiting reactant problems, the masses of product can be very close to each other. In this case, they're not, but I always want to demonstrate and emulate the best practices for these types of problems. Okay, so we'd expect theoretically 142 grams of aluminum oxide. So now if we want to calculate the percent yield, so the percent yield is going to be equal to our actual or our experimental yield, which is 125 grams, over our theoretical yield of 142 grams times 100%. So punching that into our calculator, we get a percent yield of roughly 88.0%, which is not bad. Not good, but not bad either. Okay, we have one more thing to do. We need to calculate our excess reactant. Just to get a feel for what the class thinks. Is percent yield very hard to calculate? Is percent yield pretty hard to calculate, or is it not too bad? Yeah, percent yield doesn't look too bad. It's just isolated over theoretical. So let's complete this problem, and let's say how much of our excess reactant do we have left over? So we have 200 grams of oxygen, and then we're going to subtract. We have 142 grams of aluminum oxide, and we know that in 1 mole of aluminum oxide, we have 101.86 grams. From our mole to mole ratio, we know that we consume 3 moles of oxygen per every 2 moles of aluminum oxide. Finally, we know that we have 32 grams per 1 mole of oxygen. And if we punch this into our calculator, we see that we'd have roughly 133.1 grams of oxygen in excess. Do these calculations make sense to everyone so far? Any questions on these examples? So the only thing that we've added is this little percent yield calculation. Okay, so let's test our understanding, and let's grapple. Let's grapple with an example. One moment. Sorry about that. Sometimes there's a delay when I'm streaming OneNote via Zoom. So let's look at the following example. Let's write out a balanced chemical equation. Let's predict the mass of product generated. And let's calculate the percent yield if we isolate 20 grams of iron 3 chloride. So we'll spend about 3 to 4 minutes writing out a balanced chemical equation. Then we'll spend another 5 to 6 minutes solving this problem and calculating the percent yield and theoretical yield for this reaction. So don't be shy to submit your responses via Canvas in Canvas Quiz 6.9, and then we'll discuss this example momentarily. But first things first, get your balanced chemical equation set up. That is the backbone of stoichiometry problems. And the balanced equation that I see in the chat looks perfect so far. Let's keep trying to write out the formulas and balance our chemical equation, and we'll discuss this example in about another 2 to 2.5 minutes. You know, it's always amazing when you go through this chapter, realizing how much faster you're getting at balancing chemical equations. It's really wonderful seeing that progress. So we'll discuss this balanced equation momentarily. So let's keep working on trying to write out a balanced, valid chemical equation. And don't be shy to submit your proposed responses in the chat. This is exactly the type of question that you'd see on an exam. So if you can do this type of problem, you're guaranteed to get at least around 30 points out of the 100 on the next exam. So we'll discuss the balanced equation in about another 1.5 minutes. Really want to make sure people have the time to work through these problems and generate a reasonable solution. So let's discuss this balanced equation. So let's discuss the balanced equation. Hydrochloric acid, HCl, we've seen that a ton. Iron 3 oxide, so let's do that as a sidebar. So we have Fe3 plus, O2 minus. We cross our charges. That gives us Fe2O3. Iron 3 chloride, we have Fe3 plus and Cl minus. That gives us FeCl3 aqueous, and water is just H2O. Okay, so now that we have our equation established, I'd like you to always reiterate this question. Is this equation balanced? Do we have a balanced equation? Are we good to go? Are we good to go? Do we have a balanced equation? That's the number one thing you should ask yourself. No, we don't. Now, I always like to start by balancing the elements found in the least number of compounds. So let's look at iron, okay? I have 2 irons on the left. I have 1 iron on the right. 1 times what would give me 2 irons? 1 times what is equal to 2? What do I fill into the blank? What do I fill into the blank? 1 times what is equal to 2? 1 times what is equal to 2? What's the coefficient for iron 3 chloride? Really don't be shy, but I'm going to need your help on this one.
2.
2. Yep, perfect. Okay. So now our 3 chlorines times 2, we get 6 chlorines. So if we have 6 chlorines on the right and we have 1 hydrogen and 1 chlorine in hydrochloric acid, what times 1 would give us the needed 6 chlorines? What times 1 is equal to 6? What times 1 is equal to 6? And don't be shy to provide your response. I just want to make sure that we're comfortable balancing these equations. So what times 1 is equal to 6? 6. So we have 6 hydrochloric acid, and that gives us 6 hydrogens and 6 chlorines. If we have 2 hydrogens and 1 oxygen on the right, 2 times what would give us 6? Or you can think about it as 1 times what would give us 3. What coefficient do we need for water? What coefficient do we need for water? What's the coefficient for water? What? Yep, exactly right. 2 times 3 gives us 6. So now that we have the balanced chemical equation, let's take about 5 minutes and let's try to calculate the theoretical yield of product. Let's try to calculate the theoretical yield of product for this reaction. And we'll discuss this example in about 4 to 5 minutes. And the responses I see in the chat look great so far. And the responses I see in Canvas, we have a reasonable pool of responses. Let's give everyone about another 3 to 4 minutes. Let's try to get the remainder of the class to submit responses either via Canvas or in the chat. But the responses I see look perfect so far. One of the responses I see in the chat, just make sure to double check your percent yield calculation, but it's less than 100, so that means it's likely just double checking what number you plugged in for the isolated yield. Okay, we'll discuss in about another 3 minutes. So the responses I see look great so far. The majority of the class has submitted responses via Canvas or via the chat. So let's discuss this example. So first things first, we're going to go from grams of iron 3 chloride to moles of iron 3 chloride to we're going to go from grams of iron 3 oxide, Fe2O3, to moles of iron 3 oxide, to moles of iron 3 chloride, to grams of iron 3 chloride. So if we have 19.0 grams of iron 3 oxide in 1 mole of iron 3 oxide, we have how many grams? What is the molar mass of iron 3 oxide? What is the molar mass of iron 3 oxide? Would anyone like to help me out? What is the molar mass of iron 3 oxide? 87. What molar mass of iron 3 oxide? I would double check that calculation. When I punch it into the calculator, I get a molar mass for iron 3 oxide of 159.7 grams. Now for the critical juncture in this problem. How many moles of iron 3 chloride do we produce per mole of iron 3 oxide consumed? And really don't worry about if there's a small error in the molar mass calculation. I greatly appreciate when students submit their proposed responses, so that way we can talk about them. It's all a developmental process when we work through these problems. So any responses are greatly appreciated. So what is our mole to mole ratio of iron 3 chloride to iron 3 oxide? What is our mole to mole ratio? Is it 1 to 1, 2 to 1, 3 to 1? What is it? This mole to mole ratio, it's the backbone of chemistry. So what is it for this reaction? And really, don't be shy. Yep, 2 to 1, exactly right, perfect. Okay, and then we know we have how many grams of iron 3 chloride in 1 mole of iron 3 chloride. Would anyone like to propose what is the molar mass of iron 3 chloride? Would anyone like to help me out? Don't be shy to chime in. What is the molar mass of iron 3 chloride? $162.2. Good. So if we punch that all into our calculator, we get 19 over 159.7 times 2 times 162.2. That in turn gives us 38.6 grams of iron 3 chloride. Let's repeat and let's do the same calculation. This time we're going from the moles of hydrochloric acid to the moles of iron 3 chloride to the grams of iron 3 chloride. So given in the problem that we have 0.6 moles of hydrochloric acid, so we have 0.6 moles of hydrochloric acid. Let's go to our mole to mole ratio. Let's find our mole to mole ratio. So how many moles of iron 3 chloride do we produce per mole of hydrochloric acid consumed? What is our mole to mole ratio? Looking at our chemical equation, what's our mole to mole ratio? Is it 1 to 1, 2 to 1, 3 to 1? What is it? What is our mole to mole ratio? And don't be shy, it's 2 to 6, exactly right. It's 2 to 6. We're just reading off our coefficients. Okay, so continuing on now, to convert to grams, we know that we have 162.2 grams of iron 3 chloride per 1 mole of iron 3 chloride. And if we punch that into our calculator, we have 0.6 over times 162.2, and that gives us 32.4. Oops. One moment. Sorry about that. OneNote got slightly overloaded. Sometimes it happens towards the end of a chapter. Okay, so punching this into our calculator for the expected mass of iron 3 chloride, we get 32.4 grams. So which reactant is limiting? Which reactant is limiting? Hydrochloric acid or iron 3 oxide? Which reactant is limiting in this reaction? Which reactant is limiting?
Hydrochloric.
Yep, exactly right. So HCl is limiting. So if we want to calculate our percent yield, so our percent yield in this case is our actual yield, which is 20.0 grams. Where did we get that number? We're given that in the problem. Over our theoretical yield, in this case, our theoretical yield is 32.4 grams times 100%. So punching this into our calculator, we have 20 over 32.4 times 100%, and that in turn gives us a percent yield of 62%. There we go. So that's the last example that I have prepared for this chapter. Are there any questions on this example? So that concludes the chapter 6, which is chemical equations and stoichiometry. We're going to take a 45-minute break. So I'll see everyone back in laboratory at 12:45, and we'll start the next chapter and discuss the plan for the remainder of this week. So I'll see everyone in laboratory, and we'll resume and continue our discussion in laboratory.